This program deals with detailed aspects of some of the more dangerous and difficult mineral and man-made derivative cargoes. Each one is considered in the way that all bulk cargoes should be approached, using best practice to ensure that every link in the bulk cargo chain is sound. And, in order to do so, referring as the main source of information to the mandatory IMSBC code, the International Maritime Solid Bulk Cargoes Code. Particular emphasis is placed on an awareness of the risks, especially the cargo groups. Group A cargoes, which, if shipped with a moisture content in excess of their transportable moisture limit, may liquefy in the hold during passage, threatening stability. And Group B cargoes, which create hazards because of the chemical reactions that can take place, giving rise to toxic or explosive gases. In each case, the key information that we must have in order to decide whether a cargo is acceptable is laid out. And underlying everything is the principle that safety applies as much to people as to the ship, especially when it comes to using the correct PPE and the following of strict procedures such as those for entering enclosed spaces. And to keep in line with advances in technology and the introduction of new commodities, the IMSBC code is updated every 2 years to take into account the latest developments for products shipped in bulk. In this programme, we take a look at a number of dangerous and difficult mineral-based cargoes in turn, referring to the IMSBC code schedules for each, as well as hearing from leading experts. Direct reduced iron is iron ore that has undergone a process where oxygen and impurities are removed. It is more commonly known as DRI and comes in 3 different forms. Under the IMSBC code, all 3 forms of DRI are categorized as Group B cargoes, as there is a potential risk of self-heating and hydrogen evolution if handled incorrectly. This reaction comes about from the natural tendency of DRI to recombine with oxygen.
I think we're all accustomed to iron rusting. And this is essentially an oxidation reaction where the iron is trying to go back to its original basic state of iron oxide. Rusting occurs at the surface and it produces heat. And if that heat is trapped inside a mass of material, as one finds in the hold of a cargo ship, the heat can't get out and the material self-heats. Now, as you increase the temperature of a reaction, so the rate of reaction increases. And so it accelerates and accelerates in a large pile until eventually you can get the stage where the iron is in effect burning in air, producing very high temperatures, and it glows red and it's incandescent.
This process of self-heating can, in extreme circumstances, generate temperatures in excess of 900 degrees Celsius. The removal of oxygen during processing also gives some forms of DRI a porous or sponge-like structure. When in contact with moisture, especially with salt water, this porous nature can increase the potential for reoxidation.
DRI will also rust in contact with moisture, and in doing so, it generates hydrogen. Now, hydrogen is a very light gas, but it's also very, very combustible. It's very easy to ignite. It burns exceedingly quickly and produces very violent explosions.
In recent years, it's the build-up of hydrogen gases that have caused explosions in the holds of several ships. It's for these reasons that all forms of DRI should be treated with extreme care. In line with the IMSBC code, shippers should use the correct bulk cargo shipping name, or BCSN, when offering DRI for shipment. However, this is not always the case, and occasionally different names are used, making identification of DRI sometimes confusing.
Be sure that you are aware of the nature of the cargo that you're actually being offered to ship. Vigilance is required, and if in doubt, refer the matter back to the owner, who will seek advice from his P&I association.
Correct identification and the accuracy of the accompanying shipper's documentation are vital, since each of the three types of DRI has different characteristics. DRI-A is direct reduced iron that has been densified by compaction and comes in the form of hot moulded briquettes. It's the densest and least reactive form of DRI, but may still give off flammable hydrogen gas after contact with water, especially saline water. The documentation we receive for DRI-A must certify that the cargo has moisture content of no more than 1%, and that no more than 5% of the cargo is made up of fines or small particles. It should also have a loading temperature below 65 degrees Celsius. DRI-B is the most common form of direct reduced iron. It's far more porous in nature and commonly comes in the form of lumps and pellets, as well as briquettes. As with DRI-A, DRI-B can also produce hydrogen, but it is far more reactive to water and air, and is therefore more susceptible to self-heating. The maximum loading temperature for DRI-B is also 65 degrees Celsius, but its moisture content should be below 0.3%. DRI-C is the byproduct of producing both other types of DRI, and often comes in the form of small broken fragments or fines. In most respects, DRI-C is also treated in the same way as DRI-B. As though the particles are smaller, the potential for reactivity to moisture is the same. And again, with a very low moisture content limit of below 0.3%. The IMSBC code provides all the necessary information for the correct handling and safe carriage of all three individual forms of DRI. There are also some general conditions common to all types. With all forms of DRI, the cargo should be stored ashore in an area with good drainage. And access must be allowed for the vessel's representative to inspect the stockpile. The vessel's holds should be clean, dry, and checked for watertightness before loading. Likewise, DRI must not be loaded during periods of rain, or if its temperature has risen above 65 degrees Celsius. This should be continually monitored at all stages of the loading operation. All forms of DRI are also likely to generate dust. For this reason, engine room and accommodation ventilation should be set to internal circulation. And suitable precautions should be taken to protect sensitive electronic equipment and deck machinery, as well as personnel working in the vicinity.
The dust will inevitably settle on surfaces on the vessel, on the main deck and pipework, and this is very aggressive to paintwork. It is therefore essential that the DRI dust is washed off at the earliest opportunity to prevent excessive rusting.
The taking and recording of regular cargo temperature and hydrogen concentration readings is also most important when carrying any form of DRI, as this will indicate the early signs of self-heating or explosive hydrogen gas forming. With DRI-A, surface ventilation, either mechanical or natural, is permitted. But on no account should air be directed into the body of the cargo. The carriage of both DRI-B and DRI-C is more complex. Significantly, as the risk of self-heating and hydrogen evolution is much higher, DRI-B can only be carried under inert conditions. DRI-C, unless shipped under the provisions of Section 1.5 of the IMSBC Code, should also only be carried under inert conditions.
If you reduce the oxygen concentration in the atmosphere, then you can inhibit the auto-oxidation process and prevent the hydrogen forming a flammable atmosphere. Therefore, the intention is to reduce the oxygen concentration within the cargo hold to levels that contain less than 5% oxygen. This process is called inerting, and effectively you're displacing the air and replacing it with an inert gas such as nitrogen to achieve the desired conditions.
An inert blanket is produced by filling the cargo space with nitrogen through pipework arranged in the hold bottom. Once loading has been completed, the nitrogen is introduced into the holds and all hatches sealed to produce an inert atmosphere of less than 5% oxygen. The inert condition, along with temperature and hydrogen concentration levels, should be monitored at regular intervals. And in order to maintain the inert condition whilst at sea, the cargo space should not be ventilated. Instead, it must remain sealed, requiring adequate supplies of sealants or tape. When scheduled to load any of the forms of direct reduced iron, ship's personnel need to be careful to follow the procedures laid down in the most recent edition of the IMSBC Code. It's a cargo that, especially in the B and C variants, has been the source of some serious incidents. Cargoes of fertilizer based on ammonium nitrate come in 4 different variants. Under the IMSBC Code, 3 of the variants are classified as Group B cargoes, as they possess a chemical hazard. They are also classified as dangerous goods under the IMDG Code, as they are oxidizing agents with specific procedures relating to segregation and stowage. And even though the 4th variant is classified as Group C, under some circumstances it too can create a hazard. The main risk is that of fire, which causes the cargo to decompose. All variants will then give off toxic gases, and 2 of them are also prone to explosion.
With ammonium nitrate-based fertilisers, whilst they're not themselves combustible, they can undergo, when heated, decomposition, and if allowed to continue, can actually reach temperatures of about 500 degrees Celsius. Now, there is a distinct difference between decomposition and combustion. The 2 phenomena are quite separate. It is not burning, it is decomposing. Now, during the decomposition, the chemicals which make up the fertilizer break down to produce a wide range of toxic gases. If chlorides are used in the formulation, we'll get chlorine gas given off, which is very highly toxic. hydrogen chloride, and if there are sulfates in the formulation, we'll also get things like sulfur dioxide being produced. All of these gases are produced in copious quantities, and they are toxic.
The differences between the variants come from their chemical makeup. Very often, there's nothing visible that can help us identify which is which. So it's critical that the documentation we receive about the cargo is accurate and complete.
In terms of paperwork, it does rather depend on precisely which cargo is being carried. But at the very least, there should be a bill of lading and a full cargo description, which tells what the UN number is, the IMDG classification, and most reputable shippers will also provide fairly detailed instructions as to handling procedures and the procedures to be taken for safe carriage.
And the second one is ammonium nitrate.
Okay.
Two of the variants, UN 1942 and UN 2067, shouldn't be loaded if the cargo temperature is above 40 degrees Celsius, and a certificate to that effect should be included in the shipper's documentation.
Yes, and temperature of the cargo.
But the paperwork doesn't stop there.
Depending on the actual type, some additional certificates may be required. For example, with UN 2067, there is a UN test which measures the resistance to detonation, and the material for shipping in bulk will have to pass that test. With regard to UN 2071 cargoes, a certificate indicating that it has passed the requirements of the trough test will also be provided.
Regardless of their classification, all sources of heat must be kept away from ammonium nitrate-based fertilizers. So it's essential that smoking restrictions are in place both during cargo operations and on passage, and that there's no welding, burning or other hot work anywhere in the vicinity of the cargo. Lights and electrical circuits in cargo holds should be switched off or isolated prior to loading, and should remain off whilst on passage. For the same reason, the cargo space should be separated from any combustible materials. And as ammonium nitrate is an oxidizing agent, standards for hold cleanliness are high, as any source of contamination, such as oil, will accelerate decomposition. This will also mean that bunkers and fuel oil can only be taken before loading, and the fuel tanks and pipework beneath the cargo space should be checked for leaks, whilst the heating of fuel oil tanks will need to be reduced. As there is an ever-present possibility of toxic gases, ships also have to carry protective clothing and self-contained breathing apparatus. As ammonium nitrate is a free-flowing, non-cohesive cargo, the angle of repose should be a significant consideration while loading and trimming. And in common with a number of other non-cohesive cargoes, it is also hygroscopic.
If a substance is hygroscopic, it means that it has an affinity for water and will absorb water, whether from the atmosphere or from rainfall. And some chemicals, and ammonium nitrate is one, is a chemical which does have a great affinity for water, rather like a sponge absorbing water that's poured onto it. And so it's very important that the cargo is kept dry, and clearly loading during rain should not be permitted. If it does get wet, the cargo will cake, and in extreme circumstances it can actually set like concrete.
Ammonium nitrate is commonly used as a basis for fertilizer, but it also has a number of industrial applications, including its use in the manufacture of certain types of explosives. Therefore, due to their nature, UN 1942 and 2067 also carry a potential security risk. This will involve increased security patrols and restricting access to visitors as specified in the ISPS code. The worst recorded case of an accident involving ammonium nitrate took place in Texas City in 1947. Whilst loading, a ship caught fire and exploded. The shockwave was felt more than 50 miles away. 600 people lost their lives, and nearly 1,000 buildings were levelled. Safety procedures ashore and at sea have come a long way since 1947. But ammonium nitrate is still a cargo to be taken extremely seriously.
It is important to follow the recommendations of the IMSBC code and to be fully familiar with the cargo that's being dealt with. And so long as sensible and specified precautions are taken, there shouldn't be a problem.
Concentrates are the refined ores of minerals such as lead, iron, zinc and nickel. In the IMSBC code, many appear under one schedule, the mineral concentrates group, whilst many unrefined ores, such as nickel ore, will have their own schedule. Such cargoes are categorised as Group A, cargoes liable to liquefy if shipped with a moisture content in excess of their transportable moisture limit. In other words, if the moisture content within the cargo is too high, the process known as liquefaction can occur.
What starts out as initially appearing to be either a dryish or damp cargo then behaves very much as a liquid, so that the cargo can shift. As the ship, for example, rolls in the sea, the cargo can shift to one side and not move back again, and that can result in instability, and ultimately it can in certain instances result in the capsizing of the ship.
In recent years, there has been a spate of capsizes as a result of iron ore fines liquefying. And in one 6-week period, 3 ships were lost due to nickel ore liquefaction. Indications suggest that these cargoes were all loaded with excessive moisture content levels. Cargoes such as nickel ore, iron ore fines and manganese ore fines are particularly susceptible to liquefaction. These ores are made up of fines or small particles and may have higher moisture content than concentrates. There is a reason for this.
Well, the main problem is rainfall. Many of these cargoes are mined in tropical regions where they have monsoons and heavy tropical rainstorms, as a result of which the stockpiles at mines and at ports can become soaking wet.
It should always be remembered that if stored in the open, a cargo could have been affected by recent weather conditions, potentially increasing the moisture content. So before loading commences, it's vital that we receive documentation from the shipper which contains accurate and recent figures. Concentrates and ores prone to liquefaction should have a moisture content figure below the transportable moisture limit, or TML. Figures for moisture content, the TML, and the flow moisture point must be certified in the shipper's declaration. But what do these figures actually mean, and how are they determined?
The flow moisture point, or FMP, is defined as the minimum amount of moisture in a cargo that will cause it to flow. In other words, it liquefies. That moisture content determination should have been carried out as near as practicable to the time of loading the cargo, and never more than a week beforehand.
The figures and certification provided should be the result of testing work carried out by a shore-based lab. The lab should be approved by the shipper and the vessel's representatives, as well as being recognised by a competent authority. Details of these test procedures can be found in Appendix 2 of the IMSBC Code, and it's in the best interests of ship's personnel to have an appreciation of the processes involved. Typically, during the testing process, a representative sample of the cargo is screened and divided into 3 portions. One portion is placed into a drying oven to determine the actual moisture content of the sample as received. The other portions are used to determine the flow moisture point and TML.
You take a portion of the cargo and place it in a mould which is shaped like a flat-topped cone. The sample's pressed into the mould and then turned out onto a flow table. That's a piece of equipment which is used to vibrate the sample up and down over a short distance throughout a 2-minute period. If the sample is below the flow moisture point, then the sample will break up into small pieces and bounce around on the table. If that happens, you can then take the sample again and add a known amount of water to it, and then repeat the test. If the same happens again, then you add more water, until you reach the point where you achieve flow. Obviously, being an experimental method, there is some degree of error in the method, and so in order to account for this, the IMO have introduced the concept of a transportable moisture limit, or TML, which is 90% of the value of the flow moisture point. So, for example, if the flow moisture point for a particular cargo was 10%, then the transportable moisture limit would be 9%, and one would have to ensure that the cargo that you're about to take on board has a moisture content below 9%.
A cargo prone to liquefaction must only be loaded with moisture content below its TML. But it's a sad fact that occasionally shippers' documentation cannot always be relied on to be accurate or even truthful. There are, however, obvious signs which may indicate doubt as to a cargo's condition before it's too late.
Usually these doubts arise because the captain sees evidence of excess moisture. So he should always be looking out for signs of standing pools on top of the cargo. He should also be looking to see whether the cargo, any parts of the cargo that's being loaded is darker than the rest, because it could be an indicator that there's more moisture present.
With nickel ore, these dark patches can be the result of stratification, or layers within the ore that are wetter than those at the surface of a pile. If loaded, this could lead to potential instability within the stow.
Another useful indicator is when the grabs drop the cargo into the hold, he should be looking out for any signs of splattering of the cargo against the sides of the hold or on the tank top, because that can be an indicator of liquefaction.
If ship's personnel are in any doubt as to the condition of the cargo, they can conduct their own test. This is known as the can test and involves striking a container half filled with a cargo sample 25 times on a hard surface. If, as a result, there's liquid on top of the ore, it will indicate that the cargo could be unsuitable for carriage.
If you do see signs of flow or there's any standing water, request that loading be suspended temporarily, and it's imperative that a representative sample of the cargo to be loaded is then retested in order to confirm the flow moisture point and therefore the transportable moisture limit.
There have been cases where the can test has been used by shippers to pass a cargo as fit for carriage. The can test can only indicate that a cargo exceeds the flow moisture point. It cannot be used to determine that the actual moisture content is below the TML. Therefore, any cargo that fails a CAN test must be retested in a lab to accurately establish both the actual moisture content and TML. As with any commodity that's affected by water, cargo handling should only take place in dry weather. And if recent cleaning of the holds has taken place, they should be checked for moisture content before loading. Concentrates are often very dense, so it's also important to ensure an even distribution of weight during loading. At sea, ventilation should remain closed. The priority is in making sure that the hatches are weathertight at all times.
One should be particularly mindful following any very heavy weather that there's been experienced by the vessel, because shipping seas over the hatch covers could result in water getting into the cargo.
Mineral concentrate and all cargoes should be treated with considerable respect. The schedules for these cargoes are updated every 2 years, so it's vital an up-to-date copy of the IMSBC code is consulted at all times to ensure that ship's personnel do not accept a cargo which could be unsafe. The world is still reliant on fossil fuels for much of its energy production and industrial manufacture. Annually, global coal production amounts to around 6 billion tonnes, with a high percentage being transported by sea. But though it's a very familiar cargo to many seafarers, it can sometimes be forgotten that coal can be both dangerous and difficult to handle.
The two principal risks are the potential for self-heating, which is an oxidation reaction, and the potential for generation of methane. With some coals, particularly high sulphur coals, there may be associated corrosion problems, particularly with a wettish cargo, which can cause problems for the ship structure. And with very, very fine coal cargoes, there may also be a potential for liquefaction.
This combination of risks makes coal an unusual cargo, in that it's classified under the IMSBC code as Group B, as well as Group A. That is, the main risks are associated with chemical reactions, but in some circumstances, coal can also liquefy. The risk of liquefaction is most likely when coal is largely made up of fines. In terms of chemical reaction, most forms of coal give off methane, which is easily ignited by a spark. Some coals react with air, resulting in oxidation, leading to oxygen depletion in the hold and the potential for self-heating. And high sulphur content coals can corrode unprotected surfaces. The severity of these chemical reactions varies according to the type of coal. Coals are ranked by geological age. Higher-ranking coals, such as those in the Anthracitic range, are geologically older and extracted from deep mines. These hard coals contain a high proportion of carbon and are generally very stable. Lower-ranking coals, such as lignite or brown coals, are much younger in geological terms. These coals are found much closer to the Earth's surface and, significantly, are more porous in nature, being particularly prone to oxidation and subsequent self-heating. So, as grades of coal can vary considerably, it's important that the documentation provided by the shipper is accurate and complete.
Every coal cargo should be accompanied by a shipper's declaration, which specifies the nature of the coal that is being offered for loading. At the very minimum, this should include a general description of the coal, the moisture content, the sulfur content, and the size of the coal, and in particular whether there is any tendency of the coal to self-heat or generate methane.
The IMSBC code should be consulted every time a coal cargo is to be loaded. The schedule for coal and its following appendix contain all the necessary safety information and requirements for its safe loading and carriage. For example, coal must always be stowed away from sources of heat or ignition. It should also be trimmed as flat as possible in order to prevent air being drawn into the cargo, leading to possible oxidation and self-heating. And coal must never be loaded if its temperature is above 55 degrees Celsius.
Any cargo that's in excess of a temperature of about 55 degrees Celsius should be rejected for loading. Quite often it can be identified simply by looking at steam or vapours that are being generated by the cargo. And clearly, if there's any evidence of actual combustion, the hot coal should not be loaded.
Since the temperature of the cargo is a significant factor, the ship must be equipped with the ability to measure it several times a day, both during loading and whilst at sea. The atmosphere of coal cargoes must also be continually monitored to keep in check any chemical reactions taking place in the hold. The result of these reactions can give rise to toxic or explosive gases, such as carbon monoxide or methane. Therefore, it's essential for bulk carriers engaged in transporting coal to have instruments for measuring the presence of gas, without going into the cargo spaces. Under the IMSBC code, it is a mandatory requirement that multi-gas analyzers must be fitted with the correct diameter collar to fit the gas sampling point. This ensures a tight fit and eliminates fresh air entering back through the sampling point, which might prevent an accurate reading being taken. Accuracy of the readings is vital, and a daily log of both temperature and gas readings must be kept, as this will highlight any incremental changes taking place. If carbon monoxide shows a steady increase, it could be a warning sign of the coal self-heating.
In the early stages of self-heating, one of the byproducts of the process is carbon monoxide. And in fact, this is a much more reliable method of checking whether a coal is self-heating, because if you haven't got a temperature probe in the right place, you're not going to pick it up in the early stages. But if self-heating, wherever it's occurring in the cargo, carbon monoxide will find its way into the hold atmosphere and can be picked up at a very early stage.
Likewise, coal liable to give off methane needs adequate surface ventilation. But over-venting can also lead to oxidation and the possibility of self-heating.
Ventilation of a hold to rid the hold of methane will in fact make the situation much worse for a coal that is susceptible to self-heating. The key is to monitor the hold atmospheres and only ventilate when it's absolutely essential to do so.
The correct balancing of the hold atmospheres is one of the most important factors in the safe transportation of coal. But it should never be forgotten that the gases produced are also life-threatening. Areas in the vicinity of cargo spaces should always be checked for the potential build-up of methane and carbon monoxide. This should also include accommodation areas directly adjacent to cargo hold bulkheads. For the same reasons, it's essential to follow rigorously procedures for entering enclosed spaces.
Any space in which there is coal, or any adjacent space which might be connected, will not be safe for man entry. it is absolutely important before man entry into any of those spaces which are carrying coal that the atmosphere is properly monitored to make sure it is safe.
There have been incidents of coal cargoes heating spontaneously, but in most cases, advanced self-heating and even the earliest stages of combustion can be controlled by sealing the hold. Any continuing activity within the coal will then rapidly use up the available oxygen, thereby inerting the cargo space and suppressing the reaction. If such a situation does arise, it is essential to seek expert advice on the most appropriate course of action to take before it is too late. So whilst coal may be a common cargo, it's also unique in the number of different hazards that it can give rise to. However, if the procedures laid down in the IMSBC code are followed, ship's personnel can aim to eliminate the risks.
I can't overemphasise the importance of having an up-to-date copy of the relevant IMSBC code. And not only to have it on board, but to have read it thoroughly and to have understood it. Irrespective of the nature of the precise nature of the coal that's being carried, however reactive, however much methane is being generated, those coals can be carried safely if they're carried properly.
There are many more potentially dangerous and difficult mineral-based cargoes contained in the IMSBC code. Some, for example, like sulphur, differ from many other cargoes in that the principal hazards are to human health, and from corrosion due to the interaction of sulphur, water and steel. Sulphur UN 1350 is an IMSBC Code Group B cargo, as when ignited, it's liable to give off toxic gas. Formed solid sulphur, a Group C cargo, is much safer, as its melting point is in the region of 119 degrees Celsius. But because of the corrosion hazard of any sulphur cargo, holds have to be clean, free of any residue, rinsed with fresh water and coated with lime wash or a protective barrier coating before loading. With other cargoes, such as ferrosilicon, the potential risk to the ship is so high that vessels are required to be constructed and classified specifically for its carriage. The IMSBC code should never be seen as just another set of rules. It is a vital and practical tool in reminding everyone of the hazards of many of the bulk cargoes regularly transported by sea. Nothing should be loaded and transported until everyone involved in the bulk cargo chain is 100% sure that it is safe to do so. The risks are just too great to be ignored. For more information on dangerous and difficult mineral and man-made derivative cargoes, refer to the workbook accompanying this programme.